Okay, let's go for the next chapter. The next topic is gonna be light interference. Okay, let's see what happens when we have two pulses and they interfere, they meet. For example, let's say that this is a pulse, right? We have another pulse right here, right? B2, again we're dealing with pulses. Okay, perfect, and now they meet. For simplicity, imagine that they have the same amplitude, right? Right, the same amplitude, perfect. Now before they meet, right, they get this position, correct? And when they meet, right, we have this interference. Imagine for this case, I guess it's gonna be twice the amplitude, because we are saying that at the beginning they have the same amplitude A. Great. Now after that, what happens? Well, after that, these two pulses keep moving as nothing happens. Now there's gonna be B2, let's say, and B1. Right here we have a constructive interference, right? Constructive interference, correct? Now let's see what happens when we have destructive interference. Well, in this case we have a pulse in this direction, right? And we have a pulse upside down. We say that this pulse is 100 degrees out of phase respect to this one. Perfect. If we label this again B1 and this is B2, what happens when they meet? Well, just before they meet, they make this shape, right, like this, correct? This is B1 and this is B2, correct? But when they meet, right, they cancel each other. Great. After that, they keep moving as nothing happens, right? This is B1 and this is B2. One more time, right here we have a interference, but in this case we have destructive interference, right? Destructive interference for this case. Okay, now let's use this concept to study the case when we have not only a pulse but a beam, right, of light, right? Two sources of light that interferes in one point. Let's see what happens. When do we have constructive interference, and when or where do we have a destructive interference? Okay, let's do it. Again, imagine that we have two sources. We can do this if we have sources that are in phase. For example, sound. We can create sound, right? And with two speakers that are in phase, so we can create kind of a constructive interference. But in this case, let's work with light. Light's a little bit harder to do it. Another example is using water, right? When we have water, right? Water waves, right? Imagine the wavefront, correct? If we may pass water through this opening, two openings like this, right? Correct? The water is coming in this way. What happens to the shape of the water when it goes through this opening? Well, imagine that we have something that is helping us to pull, right? This, imagine it's a string right here, and we pull it through the hole, another through the hole. What should be the shape? Well, the shape not gonna be like this. Look, there's the shape, right? Through the hole. When they go to the other side, right, they take that shape, like that, right? And then what do we have? Interference. We have this source interferes, let's say, with this source. Again, this is possible because all of these points are in phase. They belong to the same wavefront. So these are in phase, correct? And when that happens, we create a very nice pattern right here. Okay, great. Also, we can have two points, right, that vibrate at the same time, right? In water, it's very common to see this as a demo, right? We have water and we have two points, and they vibrate at the same with the same frequency, and they're in phase. Right, they produce a very nice pattern, right? Constructive and destructive interference, right? So what do we have then right here? Imagine that we have a screen where we have constructive and destructive interference, right? Perfect. Again, this is a quality of waves, right? When we have waves, like ocean waves, we create this pattern. Now, one experiment was done a long time ago that shows that actually light also produces this pattern. If light produces this pattern, right, like a wave, it means a light is a wave. And that's why this experiment is very famous, because this experiment shows that light behaves as a wave. And this is called the Young double slit experiment. Yes. Let's do it. Let's do it. Let's try to find then how this experiment was done, and the formula will help us to find at which point we have constructive and destructive interference. Let's do it. Okay. Young's double slit experiment. Young double slit experiment. Okay, let's do it. Let's do it. My brain is so fast. Okay, it's okay. That's not working. Okay, let's do it. So in this case, we have a for us we use laser, right? Imagine you have a laser right here. We have these slits right here. These are the slit, right? So we have light coming in this way, and we have a screen right here. Correct? Perfect. Now, this opening behaves as a source, and this opening behaves as a source too. And these two sources are coherent, are in phase. Okay. Now let's see what happens. This is the condition. At the center, right? Always we have a constructive interference, right? Constructive interference. If we're dealing with light, it means we have a bright spot. These spots are called fringes, right? So we have right here a white fringe. Okay, perfect. We label this M, right? That's the way how we label the fringes, right? Also, these are called the order number. Okay, for the center is called M equals to 0. Again, at the center, when the distances are the same, right, from the sources, always we have the constructive interference. Again, when these two sources are in phase. If these two sources were out of phase 100 degrees, at the center, we are supposed to have a dark fringe. You are dealing with light, right? Dark fringe, because they're supposed to cancel each other at that point. But in this case, because two are in phase, they construct or interfere constructively at that point. Okay, perfect. What happens at different points, like right here? Great. At that point, well, let's see what happens. We have a ray coming from this source and another ray coming from that source. Now let's see what should be the condition to have a constructive interference, the same thing as we have it right here at the center. What is the condition right here at the center? Well, the distance from the sources is the same. Now let's create the same condition right here. Okay, from here to here, we make a isosceles triangle, right? Now these two sides are the same, so these two distances are the same. If these two distances are the same, right, we expect to have, right, a constructive interference, correct? But look, they are not the same. What is the difference? This part. So this part must be the clue. Okay, this part is actually the change. We call this L1 and this one L2, right? So this is a change in the distance equals to L2 minus L1. Perfect. And what is the condition right here? Well, the condition is that this difference must be a whole numbers of wavelengths, correct? Because remember, when we have a wave right here, imagine this is the wave, the distance from one peak to another peak rate is called lambda, right? If we have these two waves and the difference between these two waves right here is a whole number of wavelengths, we always get that the two peaks, right, or two throbs, right, meets at the same time at that point. So we're creating a constructive interference. Okay, so again, what is the condition? That this difference must be equals, that difference must be equals to a whole number, right, a whole number of lambdas, of wavelengths. Okay, great. Now let's work with this triangle right here. Look, we have this triangle in this way, right? This is the right angle, and the distance right here is called D, the distance between the two slits. Okay, great. Now we call this D, and what else? We call this the angle theta. Correct. This is the angle right here, angle theta right here, angle theta, or this one theta, the same thing. This is more angle. Okay, great. Now, what do we have? How we can create, right, or find that section, this part, which we call it delta L. Okay, let's do it. So we use sine function, right? So sine theta is equals to the over, let's call this x, right? Or delta L. Okay, delta L. Okay, delta L. Perfect. How should be delta L then equals to? It's gonna be, let me see, that's correct? No, that's not correct because it's gonna be opposite. Again, opposite is delta L and hypotenuse is D. Okay, good. Now, what do we have then? We have that delta L is equals to D sine theta, correct? But this delta L is equals to this must be equals to that. So we have the condition for this Young double slit experiment, right? Is that to get a constructive interference, we need to have this relationship. This sine theta is equals to 2m times lambda. Okay, and when right, m takes the values for, where's m? Okay, right here. M takes the values for 1, 2, 3, and so on, right? We can create the constructive interference right here, right? And that's the condition. Again, it goes in this part. This is constructive, destructive, constructive, destructive, right? Constructive, destructive, and so on. Or when we're dealing with light, this is bright, dark, bright, dark, bright, dark, bright, dark fringes. Okay, perfect. Now, usually because this angle is very small, in the experiment we use these quantities. Look, one more time. We call this distance now L, the distance from the screen, right, to distance from the slits, right, to the screen. This is now the screen, right, screen, right, is L, and also from the center to one of the points we're looking for Y, right? Now we create a triangle, right? We create a triangle, kind of this, right? This is L and this is Y, right? This is the triangle that we create now. This is theta, but this angle is very small. This angle is very small. Okay, now for small angles, right, we use this relationship, right? Sine theta is about tangent theta. Now we can go back to this equation, right, and substitute this quantity. So what do we have then? We have that the tangent theta must be about, right, m times lambda. Okay, great. But what is tangent from here? Is y over L, right? So what do we have then? This is dy over L is equals to m lambda. Okay, usually these values are provided, are given, and it's easier again, or it has more information when we use this equation, right? dy over L equals to m times lambda. Perfect. Now this is the case when we have again a constructive interference. Yes, constructive interference. What about destructive? Again, when we have constructive is when these two waves are in phase, right? And they meet at the same time. Could be the peaks or the troughs, right, at the same time at the same point. But what happens if they are out of phase, the sources, right? They're out of phase and they meet, right? One is, right, the peak, and one is on the trough, right? So they are out of phase 100 degrees. So in that case, we create a destructive interference. And what is the difference? The difference is 1/2 lambda, right? Perfect. So then it'll be equals to m plus 1/2 lambda. Again, it's gonna be dy over L. In this case, we have a destructive, right, interference. Again, these are the conditions how we can predict, right, or find the nature of the interference, constructive or destructive, or we can say bright fringe, right, or a dark fringe, right? And again, when we have the pattern, right, produced by interference, right, we can label it in this way. At the center, right, we have white, later we have dark, right, white, 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 right, white fringe. At the center, right, is equals m equals 0, the next m equals 1, m equals 2, right? The same thing happens in the other side, m equals 1, m equals 2, right, and so on, right? Some books, right, give this as negative, right, -1, -2, the idea is the same, correct? The idea is the same, because it's positive or negative, the idea is the same. Just be careful. In general, we're dealing with magnitudes, okay? Perfect. So again, this is a very famous experiment because this shows that light behaves as a wave. So light must be a wave. Perfect. Now let's go to the next topic, which is let me see, thin films interference. Let's do it. Let's do it. Perfect. Okay, let's go for the next topic. By the way, in most of the physics classes, most of the time, right, we have this experiment as one of the most important experiments. Why? Because this experiment shows that light behaves as a wave. Because before it was believed, according to Isaac Newton, right, that light behaves as a particle. Okay, great. Today we know that actually light behaves in these two ways. Sometimes behaves as a particle and sometimes behaves as a wave, depends. Right? Okay, great. Now let's go to the next topic, which is thin films interference. Yes, thin film, right, interference. Okay, great. Let's do it. Let's do it. Look, this is a case when we have use some very small films, right, on a transparent medium. For example, imagine that we have a glass right here, right, when you're wearing your glasses, right, correct, and we have a film that is used, right, to cover, right, the glass, right, and it could have different function. Maybe it reflects, right, or the light, or partially reflected, and so on. Okay, let's do it. Imagine that we have glass right here, glass, right, and right here is a film, let's say soap, correct. Now let's play with the index of refraction. For soap, right, the index of refraction, let's say N1 is equals to about 1.3, for glass is about 1.52. Index of refraction, right, this is, okay, let's say N2. Okay, great. Now, let's use this condition to work with these situations. Look, imagine that we have a rope, right, and you have a pole, you create a pulse right here, a pulse, right, and this rope is fixed. This could be a wall, could be a tree, right, it doesn't move, right. What happens when this pulse is reflected? When this pulse is reflected, right, it reflects upside down, right. The same condition happens to waves, right, with light. If we have a medium right here, imagine it's a glass, right, and we have air right here, right. If we have again a pulse right here, light, a pulse of light, how is reflected? It's reflected upside down. If we have reflection, correct? Now, let's see what happens if we have again the rope, okay, rope, right? But now this part is movable. Again, we create a pulse, right? But when the pulse reaches this position, this ring, right? Like this is coming, right? Now the ring moves up and then moves down. Again, it produces a reflection too. Now the pulse is reflected, right, in phase with this one, uprighted. Right here is inverted, right, out of phase 100 degrees, and right here they are in phase, correct? Perfect. The same thing happens when we're dealing with light right here. Look, imagine that now light goes from glass, right, to air, let's say. So let's go inside. So imagine this is a pulse right here in this direction, correct? How it's reflected on this surface is reflected, right, in the same with the same phase backward, right, like in this case. Now let's apply these ideas to work with interference using this film. Okay, let's do it. The most important part right here is the wavelength, wavelength inside of the film, right? The wavelength inside of the film, right, is equals to V, right? Remember how to define speed of a wave, right? The speed of any wave is equals to frequency times lambda. Remember that part? Okay, wait. Now in this case we have that the wavelength of the in the film is equals to V, right? The speed of the light in the medium divided by the frequency. Remember, the frequency is constant, doesn't matter of the medium, transparent medium, right? Now what happens to V? Also, let's relate V to the index of refraction of the medium, right? Remember, N is equals to V to C, right? To C over V, correct? Okay, great. Now when we solve for V, what do we have? Let's plug it right here. Okay, let's do it. So V then is equals to, let me do it right here, right? V is equals to, this is equals to, is it correct? Yeah, it's correct, right? This is equals to C over what? C over N, right, times frequency. Which N is this one? N of the film, right? Of the film. Film, perfect. Got it? Okay, great. So this is gonna be then the lambda of the film. But what is C? One more time. C right here is equals to what? Frequency times lambda in the vacuum, correct? So this is equals to what then? This is equals to frequency times lambda, right, on the vacuum. And finally, what do we have? We have the lambda in the of the film, right? Film is equals to what? This is divided by what? Let's continue. N of the film, right, times times frequency. Okay. We have too much time. Okay, let's do it. So what do we have? The frequencies cancel, and we have lambda the film is equals to lambda, right, vacuum divided by the index of refraction, right, index of refraction of the film, index of refraction of the film. Okay, perfect. Now let's use again this idea, this concept, to explain what is happening right here. Okay, let's do it. Okay, imagine that we have light. We have light, right, in this way, right? Imagine. But look, this index of refraction is, let's say, N1, and this is N2. Okay, N2 between these two. But one more time, I will explain before, because this index, right, is more than this one, right? Like when we have glass, again, glass and air, remember we explained it. If we have a pulse in this way, it is reflected, right, upside down. So this one is reflected out of phase 100 degrees, right? So it means it's gonna be in this way, right? This is going down, this is going up by this interface. Now what happens? Well, let's go to the next interface right here, correct? This is transmitted in phase, again, in phase, like this. But one more time, look, we have this index of refraction is less than this one, like right here. This one is less than this one. So it's reflected, right, out of phase, correct? Now this one, this light is reflected by this surface, right, again, out of phase respect to this one. So it's gonna be again in this way, right? In this way. But this is out of phase respect to this one. Also, this one is out of phase respect to this one, means that these two are in phase, correct? These two are in phase, out of phase like this. Now these two are gonna be in phase, correct? So these two are in phase, and these two we have interferences, interfere constructively, and we see light. We see a lot of light coming from that glass, from that lens, let's say. Got it? Okay. Because of this condition. Now, what happens? What should be then, one more time, the condition to create constructive interference? Well, the same thing as we did before, right? Remember, using the double slit interference, right? In this way, we mentioned that we're looking for the difference. The difference in length must be equals to whole numbers of wavelength. The same thing happened right here, right? We have that this difference in length, let's call that length, right here we call it L, we call it right here T, the thickness of the film. Okay, now, but what happens? Look, light is coming, and is reflected. So we have actually light, the difference is twice T, because we have one T going down for this one and one T going up for the next one. So the difference between these two waves is, right, 2T. 2T is the difference. Right, 2T must equals to what? What is the condition right here? M times lambda. Now, which lambda is this one? It's the lambda of the film, right? But lambda of the film is equals to what? Is equals to lambda in vacuum divided by the universal refraction of the film, correct? Perfect. So this is the condition for this type of thin films interference, right? To have a constructive interference, right? So right here we have a constructive interference, correct? Now, when do we have destructive? Well, the same thing, it's gonna be 2t, the same thing as right here, right? When do we have destructive? When this delta L, right, is equals to m plus 1/2 lambda. The same thing happens right here, right? It's gonna be equals to m plus 1/2, correct? Lambda in the vacuum divided by n, right, in the refraction of the film, correct? Perfect. Now let's go to another condition that give us the opposite result. This one. Look, let's go again now to this condition. Okay, perfect. Again, this is T. Now imagine that in this case we have only soap. We have soap, right? We have soap again, right? The thing is T. One more time we have a wave, right, coming right in this way. As we mentioned before, correct? Because this index of refraction is less than this one, correct? One more time, this is glass right here. We have the pores in this direction. How is it reflected? Upside down. The same thing, right? Is reflected right in opposite direction. Okay, upside down, out of phase. Perfect, opposite direction, out of phase, right? Reversed. Okay, now let's go through the film. Okay, it's coming in this way, imagine. Now, right here we are going from index of refraction higher than the other one, like right here. If we have again the glass and we're going from the glass to air, right? We mentioned we are like this is reflected right in the same in phase. Okay, in phase, right? Meaning that this one is reflected right in phase. But now right here it goes right out of phase with the second one. Right, one more time. Look, this is out of phase with this one, but this one is in phase. So at the end, right, we have that they interfere destructively, right? Destructively when they join in that way. Okay, and let's do again an equation. So we're looking for the difference in the distance, right, in length, and the difference against 2t. We are explaining right here. Must be equals to what? Must be equals to whole numbers, right, of lambda, correct? But in this case, when that happens, we have destructive interference, right? It's the opposite, right? And this is equals to what? Which lambda is this one? Film, right? It's this one right here. So it's equals to what? Lambda in vacuum, right, over index of refraction of the film, correct? And this is a case for a destructive interference because they distract over there. Now, when do we have a constructive? It's gonna be right in this way. So it's gonna be m plus 1/2. Right, when we add the subtract 1/2 of the wavelength, right? Lambda in vacuum, right, divided by index of refraction of the films, right? And in this case, this is right the condition for constructive interference. So as you can see, look. This is the same as this one, but for this case it's constructive and for this case it's destructive. This one, right, is the same as this one, but in this case this is destructive and in this case it's constructive. So it depends, right? Depends if we have these three systems, let's say air, the film and glass, or if we have only air and the film, correct? We create again the conditions for a thin film interference. Okay, let's start right here and I'll see you in the next video. Okay, bye.